I'm really pleased to introduce this week's speaker. It's Saul Friedberg from Boston College, and he'll speak on extending the theta correspondence. Saul.
Great, thank you. I'm going to share my screen now. Okay, just checking. Can everybody see that okay?
Yep.
Good. Okay. So I'd like to thank Kumar very much for the opportunity to give this lecture. In fact, I've never spoken in Toronto, but I've had many wonderful conversations with mathematicians from Toronto. And it's a real pleasure to complement that by having a chance to present some work at this seminar. So this work is going to be based on joint work with David Ginzburg from Tel Aviv University. And let me give you a plan for the talk. So I want to begin by talking about the classical theta correspondence. And here it will be a quick and informal review with a lot in common with Steve Kudla's talk in this seminar in June 2020. And you know, with just a focus on the particular things that I want to bring to the new work. And then in the second part of the talk, I'm going to go beyond the Weil representation. And that turns out to be an old story, but I'd like to give a quick account of it. And the way we'll go beyond the Weil representation is with minimal theta representations, other minimal representations, and then talk about non-minimal theta correspondences, which is a bit less well known, but there's some older work and some more recent work to talk about. And so those first three topics will take us through roughly half the lecture. And then in the second half, I'll turn to the new work, which is joint with David Ginzburg and talks about extending the classical theta correspondence to higher degree metaplectic covers. Those covers were talked about in the lecture, the pre-talk that I already presented, but I'll also give a little quick review of that in case you didn't have a chance to look at that and try to make the connection between these abstract covering groups and classical number theory, because I think it's important to keep that connection in mind. Okay, so let's begin. And let me begin with a little bit of early history of the classical theta correspondence. Even before the theta correspondence, there was the Shimura correspondence between half integral weight modular forms and integral weight modular forms, called one of them f of z, another f prime of z prime. And this was based on the converse theorem, and it was formulated adelically by Gelbart and Piateski-Shapiro. And both those authors, all of those authors talk about a covering group for half integral weight modular forms. And then the connection to theta series is due to Shintani and Niwa, who realized that you could take an automorphic form, a modular form, say, of half integral weight, and do this integral against a function of two variables and come up with a modular form f prime, and you could sort of physically move a modular form of one type to a modular form of the other type by means of this theta kernel in two variables. And this theta series, theta of zz prime, is modular in both variables, and that's what allows you to pick up something modular and make it and integrate and get something modular. And that is essentially proved by Poisson summation. And we'll talk more about those theta series and their generalizations in this talk, but maybe an early pointer to where we'll be going with this is just to make an informal remark that these theta series have lots of vanishing Fourier coefficients. Maybe classically, the classical Jacobi theta function is concentrated on squares, and I'll write that down a little bit later in the talk again. And that maybe is a signpost to something we should be thinking more about. And then the Shimura correspondence was analyzed using theta functions, and there was a local correspondence, and this was studied and analyzed adelically and tied to representation theory by Waltz Berger in his very well-known work, where he showed that the central values of quadratic twisted L functions were also an integral part of the story. And there was a choice of additive character that played an important role. And so there's a beautiful and rich theory of the classical theta correspondence. Now, this was picked up more generally, and in fact, Steve Kudla was one of the people that did that early on, and it also came up in his talk. And so the more general setup is that I might take a special orthogonal group which acts on one vector space, which is equipped with a symmetric bilinear form that's non-degenerate. And I might have a second group G prime, which is a symplectic group attached to another vector space W prime, and that space W prime is equipped with an antisymmetric form, a symplectic form. And then the game is to take the tensor product of the vector spaces and also take the tensor product of the two forms. And so one is symmetric and the second is antisymmetric. So the tensor product is antisymmetric. And so I get a symplectic group SPW. And both of these smaller groups embed in it by means of basically they act on one or the other factor in the tensor product. And so the general story which Shintani and Niwa were describing a specific case of is to take a theta function on the big SPW, and actually it's something of potentially half integral weight, so we should talk about its metaplectic double cover, and then restrict it to the image of G cross G prime inside this bigger group. And maybe I need a cover if I'm on the double cover, but basically restrict it to the image and get a theta correspondence. And in fact, the Shimura correspondence is the special case where V is of dimension 3, so it's something like an SO3, and W prime is of dimension 2, so G prime is SP2 or SL2. And in fact, because the vector space V is of odd weight, you get something on the double cover of SL2 rather than SL2 itself. And so that's the Shimura correspondence and its connection to the theta correspondence laid bare. Okay, now there was a key group theoretic aspect that was isolated by Roger Howe in this context, and he observed that G and G prime, they both act reductively on the big vector space W, and they are each the full centralizer of the other in SPW. So there's an algebraic fact which is underlying this, and so because each of them is the full centralizer, it's certainly natural to restrict something to the product of their images. And in the phrase is that GG prime is a reductive dual pair. And in this broad generality, you can produce a global theta correspondence by taking a theta function on the double cover or of SPW adelic and restrict to the embedded image of G cross G prime and use it as an integral kernel. So you can take the model of Shintani and Niwa and soup it up to more general groups. And again, Steve Kula did that in one case to get the real quadratic base change map. I did something with an imaginary quadratic base change map following Niwa, who had done other work on that. And in fact, you can do this for any G and G prime. Now, at some point, I thought I might give a survey of this. And so I Google scholared theta correspondence and discovered that I wasn't going to give a survey because there were about 271,000 entries. But the lesson here, of course, is that this is a very, very rich topic. And I just want to focus on one theme that has come out. This is an idea due to Steve Rawlis, that you can look at SPW and not just look at one SOV, but you can study a bunch of nested special orthogonal groups where you take V and systematically add to it 1, 2, or up to n copies of a two-dimensional hyperbolic quadratic space. And so you might start with something on SPW and look at the lifting to each of these groups, each of which sits inside a bigger group. And he showed that if you take an automorphic representation on the first group, then there is a non-zero theta lift somewhere in the tower. And in fact, the very first time you get something that's not zero, the lift is cuspidal. And there's a big story there. I'll talk about the local aspect in a moment, but there's a big story there. And in particular, the study of the lowest point for which the lift is non-zero, the first occurrence, the first time you get something non-zero in one of these nested special orthogonal groups is of interest, and it's related to periods of automorphic forms. And this was described in quite a bit of detail in a very nice paper by Brooks Roberts. Okay. Now, as I was mentioning, this is a global story, but there's a complementary local story, and I just wanted to spend a slide on that. And they explained that the theta series are tied to the Weil representation, which can be formulated adelically, but also locally. So we can look at the double cover MP2N of a symplectic group sp2n, and it all depends on a choice of additive character, psi, and so we often will roll psi into the notation for the Weil representation. So that's this omega sub psi. And in fact, Roger Howe talked about the reductive dual pair structure and conjectured that if one took the Weil representation and in a suitable sense restricted it to G cross G prime, then we would get a correspondence of local representations. I'll say a little more about how you do that restriction in a moment, but that was the idea. And this conjecture of Howe was very fundamental. It was proved by him for Archimedean fields, and then by Waltz-Bourget for non-Archimedean fields of odd residue characteristic, following Howe's method, and then by Gann and Takeda in 2014 for arbitrary residue characteristic. And you might think that if you just look locally and just say, look at Howe correspondence, you get a smaller story. But if anything, you get a bigger story. There are about 364,000 papers that Google Scholar attaches to the phrase Howe correspondence. Okay, so just a few things to know about it. First of all, it's functorial. We always like to see Langland's correspondence, and at least if the rank is roughly the same size, as rank is the same, then Rawless, Adams, and Dipendra Prasad in various cases addressed questions related to functoriality, which isn't true in total generality, but it's true in certain cases. And then there's a local theta tower, which complements the global theta tower that Steve Rawless described, and Steve Kudla did some beautiful work on that. And he showed that basically you can replace cuspidal by supercuspidal, so the first occurrence will be supercuspidal in the local theta tower. Okay, so this slide is entitled Beyond the Weil representation. And when you see all this and you see there's a big rich theory, you know, it's a natural question. What makes this Weil representation so special? What is it about this that's making this all happen? So let's sort of step back to the general story. So imagine I have two p-adic groups, G and G prime, and they both sit inside some larger group H. Let's say as commutators. Really, at least they commute with each other, okay? And take a representation capital theta of the big group H, and it's natural to then study the decomposition of theta into irreducible representations of G cross G prime. So let's start with pi, say an irreducible admissible representation of one of the smaller groups, and take its maximal pi isotypic quotient, which in literature is called the big theta attached to pi. And the maximal pi isotypic quotient is of the form pi tensor theta of pi for some representation theta of pi of G prime, the other smaller group. But when I say it that way, it's not at all obvious that theta of pi is a singleton. It might be a very large representation. It's not even obvious that it's of finite length. I think that's something else that Steve Kudla proved for the Weil representation. But if theta of pi isn't gigantic, then maybe the thing we started with, the capital theta on the big group H, had to itself have been small in some natural sense. So this restriction did not grow in some uncontrolled way. And David Kajdan made the observation that the Weil representation is small in a very specific sense. It's a minimal representation, which is to say it's attached to the minimal non-trivial coadjoint orbit. Now, I described that notion in some detail in the slides for the pre-talk, but if you didn't get the chance to look at them, you might just sort of intuitively think that means that lots of Fourier coefficients are zero. And we'll talk a little more about Fourier coefficients throughout this talk. Basically, there are lots of unipotent subgroups you could integrate against a character. And it says if the unipotent group is relatively large, then you get zero. You need to only integrate over a small amount, or else when you average, you get zero. And so that can be made very precise, and that was Kajdan's observation. So this brings to mind a couple of questions. And locally, we can ask, can you find other minimal representations over a local field, and then study some kind of a generalized Howe correspondence along the lines of what's on this slide? And then there's a global complement to that. Can you find an automorphic minimal representation that's not a classical theta representation? And if so, is it possible to use that to make a theta correspondence? So to do the same business of integrating against a kernel function of two variables where you integrate against one of them and get a function of the other. You can do it in either order. Where I might let theta be chosen from functions in this other automorphic minimal representation and pick up automorphic forms on one group and move them to another group by means of a similar process. So those are the questions that get brought up. Okay, any questions? All right.
It's very good.
Good, yeah. Okay, so then carrying on. So let me just say a tiny bit about a local minimal representation. Again, there was more in the notes on the pre-talk, but the local analog of a Fourier coefficient is some kind of a module where I mod out by something, and it's called a twisted Jacobi module. But the basic idea is there are these things that in some sense index possible Jordan decompositions, these unipotent orbits, and to each of them you attach a unipotent subgroup. So the largest subgroup might be, say for GLN, you just take the matrix, upper triangular matrices with ones on the diagonal. And you can do the same kind of thing for a symplectic or a special orthogonal group as well. Okay, but it might be that when you integrate over all of those, you get 0, so then maybe you need to shrink it a bit. So for each of these orbits, there is some kind of a unipotent group, and then you can define some kind of a natural generic character for that group, and you can mod out by the subspace generated by the vectors that are equivariant with respect to the U action and the character psi O, and you just do it by literally building psi of UV minus pi of UV minus psi O of UV, and you take those combinations and take the subspace generated by them, you take the quotient, and a minimal representation is one where lots of these local analogs of Fourier coefficients are 0, that you have to have a very small unipotent subgroup UO in order for this quotient not to be 0. And then Gordon-Savin and Kajdan and Savin studied local minimal representations and constructed them for p-adic fields, for Archimedean fields, work of Gross-Wallach, Berlinski-Kostant, and probably others. I'm sorry, my history won't be perfect, and there, with all those hundreds of thousands of names, I probably will be omitting some. So if I omit someone is listening to this and I omit them, I apologize. It's not on purpose, just some ignorance or an inability to fit all the work on the slides. Okay, so let's go to the automorphic setting. So the Jacobi theta function is our prototype of a theta representation. And you might sort of ask, how can you make these things? One way is by the Weil representation. And in Steve Kudla's talk, he explained how these theta representations that generalize the Jacobi theta function all arise by the Weil representation. But what if you want to go to beyond the Weil representation? You need another way to get things like this. So it turns out you can construct this theta function as a residue of a half integral weight Eisenstein series. And that's an observation that goes back to really some classical work, but maybe isn't as well known as it could be. If you take a half integral weight Eisenstein series, its Fourier coefficients are quadratic Dirichlet L functions, and so the residues are 0 unless the quadratic character is trivial, and that basically allows you to take a residue and build something supported on squares. So the Jacobi theta function is a residue of a half integral weight Eisenstein series, holomorphic half integral weight Eisenstein series. And more generally, all the theta series that come from the Weil representation are residues of certain Eisenstein series, and that's a special case of a Siegel-Weil formula, which Steve Kudla again mentioned in his talk. So the idea for constructing automorphic minimal representations is to use other Eisenstein series for other groups and take their residues, just the easiest Eisenstein series, a Borel inducing from a character of the maximal torus, and making, so if you will, from the Borel subgroup, and taking their multi-residue and getting some kind of a residue, which is L2, and that's an automorphic theta function. And that turns out to be a minimal representation in many instances. And I do want to emphasize that we lose all the structure of the Weil representation. There's not all that structure that comes in. However, we do have Eisenstein series, so we have to use those instead. And this idea of using residues of Borel Eisenstein series was already done in the 1990s. Ginzburg, Wallace, and Sudry constructed these automorphic minimal representations for any split simply laced group over a number field. Okay, and then there became a whole subject of exceptional minimal theta correspondences. Exceptional is a nice example because exceptional groups are important, but there's no Weil representation, so it's maybe an interesting place to look at this. And I put on this slide a bunch of names of people. This is only a subset of all the work. Maynard Savin, John Shuley, Dick Rosen, Gordon Savin. Again, something here related to motives of rank 7 and weight 0 with Galois group of type G2. Marty Weissman has an octonionic version of the Jacques-Langlands correspondence. Loke Savin even in 2019. And Ginzburg, Wallace, and Sudry showed that even the theta tower works in some of these exceptional cases by using an automorphic minimal representation on GE7. And Ginzburg and Zhang in 2001. And then David Ginzburg in 2019 in the Journal of Number Theory, a beautiful, very long paper, show that you can use an automorphic theta representation on the double cover of F4 and study, once again, a correspondence. So this is an area which there's been a lot of interest in and some connections to other parts of number theory as well. The last part of this slide is the double cover of F4. And so I want to now talk a little bit about covers of groups and use that as a motivation to talk a little more about covers of groups. And so here's one slide about that. That's all I'm going to put in. But once again, this was discussed in more detail on the pre-talk, but I wanted to put a slide in for people that didn't get a chance to look at that. So the story about this is that I'm going to take a number field F. You could also use a global function field, fix a number R greater than 1, and assume that my number field has a full set of rth roots of unity. And implicitly, I'll be embedding that abstract group into C cross at various points in the talk, but I won't keep track of that by notation. But I'll let G underline be a linear algebraic group over F. And then in this setup, you can talk about some automorphic forms that are on higher metaplectic groups. So what's an automorphic form? It's a function that's invariant under a discrete subgroup. So if I'm thinking classically for a moment, f of gamma g is some character of gamma, f of g. And if I'm really doing it classically, I might use something like a Dirichlet character chi of d, where my matrix is A, B, C, D. But in the higher metaplectic group story, I'm going to use some exotic homomorphisms for chi. And the simplest one is very easy to explain. If I'm on, say, a subgroup of SL2 of the ring of integers, I just take A, B, C, D to the rth power residue symbol C over D sub R. And Kubota showed a very long time ago that the map that sends A, B, C, D to the rth power residue symbol C over D sub R, if C is 0, then you just define it to be 1, otherwise it's C over D sub R. That map is a homomorphism from a congruent subgroup of SL2 of the ring of integers. And the proof of that's not trivial. In fact, it uses reciprocity. But what makes this homomorphism very different is that its kernel is not a congruent subgroup. And it's the beginning of a whole story of homomorphisms whose kernels are not congruent subgroup developed by Bass-Milner-Serre. And those are the objects we're going to be talking about. So they're very classical modular objects, except that the chi is built out of something like rth power residue symbols. That's really the right way to think of these higher metaplectic covers and the automorphic forms on them. And as I explained in the pre-talk, when you want to make these things adelic, you need to introduce this language of topological central extensions, and you need to extend the group G, either the local group or the adelic group, by the rth roots of unity in the sense of an exact sequence and a topological central extension. And there's a long history of studying these topological central extensions that go back to the work of Moore, for example, and even there's been a lot of recent work as well. And I mentioned just a couple of my favorite recent papers, Gann, Gao, Weissman, and Kaplan, just from the last few years about these extensions. So the goal of my talk is going to be to extend the theta correspondence to these exotic covering groups where I'm really talking about automorphic forms that transform under these characters whose kernels are not congruent subgroups. All right. So before I get to that story, I want to talk a little bit more about non-minimal theta correspondences. So you might say, can you go beyond minimal? And it turns out you can. So David Vaughan showed that there's no minimal representation. You cannot do it automorphically or locally for an odd orthogonal group, a nice split odd orthogonal group, SO9 or beyond. And together with Dan Bump and David Ginzburg in 2003, we showed that you can still take a residue of an Eisenstein series and construct a function which it deserves to be called a theta representation. And it's no longer minimal, but it's attached to another small unipotent orbit. So it's not quite true that every Fourier coefficient one can imagine is zero, but it still has many vanishing Fourier coefficients. And for SO9, the unipotent orbits are a partially ordered set, and it's attached to one of the next two smallest orbits, but there really are two non-comparable small orbits, in that case beyond the minimal one, just over the minimal one, and it happens to be attached to one of them, not the other. Okay, it's a residue of an Eisenstein series, it's L2, it's irreducible. There is a local story in terms of images of intertwining operators, and you can think of it in terms of images or irreducible quotients. So there's both a global and a local story of these objects, which we developed all those years ago. And just to tell you what a small but non-minimal unipotent orbit looks like, I just wanted to put a slide up about that. These unipotent orbits are described by partitions. So I'm going to be talking about partitions of 2n plus 1. And in order to make them correspond, we're not looking at the general linear group, but we're looking at a special orthogonal group, SO2n plus 1. So you have to look at partitions where every even part is repeated an even number of times, it turns out. And so here's a description of the unipotent orbit, a bunch of 2's. This is a partition. So 2 to the 2m means 2 repeated 2m times, and then there's a 1 left over. And that turns out to be the description of the unipotent orbit. And so we proved in 2003 that this theta representation does have non-zero Fourier coefficients for this guy, but all the bigger Fourier coefficients and the non-comparable Fourier coefficients in the sense of this partially ordered set of unipotent orbits, all the rest of them are zero, and we got local results. Okay? So the surprising thing is that even though it's not a minimal representation, it's still small enough that you can use it to make a theta correspondence. And so the way you do that, just to quickly describe that, is you put two orthogonal groups in a bigger orthogonal group. You can do it with double covers, but just on the level of matrices, you just sort of put the groups together in sort of a block matrix way. And then you take this theta on the big group, this non-minimal guy, but still small, and you restrict it to the embedded image, and you use it as a kernel. And that's what we did in a paper in Duke in 2006. Okay, and we show that this map is even functorial in a suitable sense on unramified principal series. And I have to tell you what functorial even means, because you have to talk about a dual group for covers. And the idea is that if it's an odd degree cover, it works like the 1 degree cover. But if it's an even degree cover, then long and short root swap. So it works a little bit differently. So that's the way it works. So there's some notion of dual groups for covers, which has been greatly expanded by Marty Weissman. And in particular, this is all split, and he's dealing with non-split. So that's the story. And I'm actually assuming that the field has the 2 nth roots of unity in it. And as Marty explained, it's a bit more complicated if it has the nth roots, but not the 2 nth roots of unity. And just for people that know about wavefront sets, you can study how wavefront sets behave under this non-minimal theta correspondence, and that's something that's never been done. But my grad student Yusheng Lei has actually just gotten, just in the last short period of time, some very nice results about that, and you can actually make some very elegant statements about how the wavefront set behaves, even with this non-minimal theta correspondence. Okay, there's one other example of a non-minimal theta correspondence, and it also involves a theta function whose unipotent orbit has lots of 2's in it. And this is work of a former grad student of mine, Spencer Leslie, who looked at the automorphic theta representation on the fourfold cover of a symplectic group, and 4 turns out to be important here. And once again, you can make a theta representation, and the unipotent orbit is not minimal, but the unipotent orbit is just 2 repeated a bunch of times. So it has a very sharp Fourier coefficient structure. And he once again used it as an integral kernel. And what sort of happens is interesting. You lift from one symplectic group to another, and there is a tower property, but this time, instead of getting something that's cuspidal, I mean, you get something that's cuspidal, but it's cuspidal and associated to a parabolic subgroup, these representations that violate the Ramanujan conjecture, so it's a cap representation. That's what he showed. And he also studied the local correspondence from ramified principal series. Okay, so that's the first half of the talk, and meant to be a survey and a framing of a lot of prior work, which I think puts the new work in perspective. And I'll just pause for a sec to ask if there are any questions before going on to the new work. Okay, so now I want to tell you about extending the classical theta correspondence to these exotic automorphic forms and transform with respect to these characters that require new groups to formulate them adelically. And this is work with David Ginzburg that just came out a short time ago on the archive. And what we will do is we will replace the classical reductive dual pair of how an even orthogonal group and a symplectic group by the R-fold cover of each of those, where R is odd. And so that's the even case. But in the odd case, if you remember, like the classical Shimura correspondence, I would have had to go to the double cover classically. That was already back in Niwa and Shintani's work, SO3, the double cover of SL2. And so here we'll take the R-fold cover of an odd orthogonal group and pair it with a 2R-fold cover of the symplectic group. So that will be the extension. And as we'll see, it's not totally straightforward. It needs some new ideas. Okay, so here's the structure behind our correspondence. And this is a complicated slide. I'm going to go over it slowly. This is the algebra that will make the representation theory work. Okay, so first of all, I'll have 2 groups, a G1 and a G2. And then we'll do this with covers. But first, let's just think about the groups, if we're saying algebraic groups. So I'll have G1 cross G2, and they will sit inside of 2 symplectic groups this time, not just one, SPW1 and SPW2. And in the first case, the iota 1 is just the sort of standard reductive dual pair, putting 2 groups inside a symplectic group. Okay, so that's the same structure that we already met and that I began the talk with in my very second slide. Again, the same structure that came up in Steve Kudla's talk as well. So that's a classical reductive dual pair. Now, there's also going to be another group in play, SPW2, and it's not quite true that they are mutual centralizers inside of SPW2, but it is true that G1 cross the identity and the identity cross G2 commute with each other inside SPW2. So they commute even though they're not mutual centralizers. Okay. Well, so since that's a little bit smaller, we get a little bit of extra structure for the second group. We have a unipotent subgroup of SPW2, and that unipotent group is normalized by the embedded image of G1 cross G2. So I embed G1 cross G2 inside of SPW2, and when I conjugate something in U by that, I end up inside of U. And not only is it normalized, but I have a character psi U, and this embedded image, acting by conjugation, stabilizes the character. And I said that they're not full centralizers, but what is true is that this embedded image is a finite index in the full stabilizer of the character inside the normalizer of U inside of SPW2. Okay, so I have these 2 groups with these 2 different algebraic structures, one a classical reductive dual pair, another a unipotent structure with a character as well. I also have a way of connecting the 2 groups. So number 4 says that I have a homomorphism script L that takes U inside of SPW2 and moves it to the Heisenberg group attached to W1. So the Heisenberg group, again, that's mentioned in some detail in the pre-talk. So it's an extension of W1 by a one-dimensional vector space, say over a local field. And the multiplication involves a symplectic form. And so there's a homomorphism from the U inside of SPW2 that links the two symplectic groups together in this specific way. It actually moves U to the Heisenberg group attached to W1. So that's the algebraic structure that I propose to use. And I'll give you an example of this a little bit later. But first, let me give you the structure. Okay, now I want to tell you about the representation theory. So here's the Weil representation again. And the Weil representation classically is a representation of the semi-direct product of the double cover of the symplectic group, the metaplectic group, with the Heisenberg group. So that's going to be something that sees the first vector space W1. That will be the classical Weil representation. And for the second vector space W2, I'm going to look at some other small representation. And that's in the sense of the earlier parts of my talk. It might not be minimal, but it won't be too large. It'll have lots of vanishing Fourier coefficients. And so the really new idea here is I'm going to take a tensor product. I'm not going to take just a single representation. I'm going to take the tensor product of these two small representations and think of it as a representation for the direct product of these two different groups attached to two different symplectic vector spaces, W1 and W2. And the proposal, which we illustrate in our paper, is that with this algebraic structure, that there, in some cases, should be a generalization of the How and Theta correspondences. And there, of course, will be local aspects, and there will be global aspects. Okay, so just to write down the structure here a little bit more carefully, let me tell you the local aspect first. So if you remember, we took a twisted Jacobi module, what we need to do is, so the classical How correspondence just says take the Weil representation and restrict it to the embedded image of G1 cross G2. But here we have this unipotent group as well. So first I have to take a Jacobi module of the tensor product. And I mod out by this complicated subgroup that interweaves the two different U actions. So on the second group, U transforms by means of a character psi U. And on the first group, we move U over to the Heisenberg group, and then the Weil representation can be applied to a Heisenberg group element, and that acts on V1. So I'm modding out by a subgroup of the tensor product, of the subspace, excuse me, of a tensor product vector space, and the subspace is generated by these combinations that really weave together the two different ways that U lives inside of these two groups. Okay, so then the proposal is that if you replace the tensor product by the Jacobi module, this twisted Jacobi module in this sense, that's the thing that should give a local correspondence. And then globally, what we do is we do an integration against the unipotent group, a Delic mod rational, and against a character. And so the theta kernel that we'll write down, and I'll put it in a slide for you, is more complicated than the classical theta kernel because we also have this complicated unipotent integration that uses the U structure on the two different groups. Okay, so I'll write that integral down a little bit later, but first let me show you the groups that we're going to use in our talk. So a lot of notation, but let me try to go through it. R greater than 1 odd tells me the degree of the cover. And you might think of R being 7, just to sort of fix your idea. And then I have a symplectic group, SP2N, and an orthogonal group, SOK. And I'm always working in this paper with split orthogonal groups. We're working, but we can write some of these things down for non-split as well. And then this so happens this number, R minus 1 over 2, called R1 is going to come up a lot. So if I'm on the 7-fold cover, R1 is 3. Okay, and I promised you 2 different embeddings of an orthogonal cross symplectic inside a a bigger symplectic. And the first one is just the thing coming from that tensor product construction that we use in the classical reductive dual pair construction. So that's iota 1, the standard thing. And the thing that came up again in Steve Kudla's talk a month and a half ago. Okay, the second embedding is just one of the ones like the ones I was showing you. You put the groups in a block form. So I'll put the special orthogonal group in a bunch of times on the diagonal, and then I have to maybe just tweak it slightly so that the corresponding matrix is symplectic. And the symplectic group I'll just put in the middle. So I'll just leave the symplectic piece alone. I'll repeat the orthogonal piece. And the fact that I'm doing a specified number of repetitions is important when I want to make this work for covers, because of the way, if you will, I said we could think of these covering groups as related to homomorphisms. And if you sort of look at this, I have R-1 copies that either H or H star is embedded. And if I have an rth power residue symbol and I raise it to the R-1st power, I get the conjugate residue symbol. So that algebraic fact plays a role, and it's related to the number of embeddings. I don't want to go through that in too much detail, but I'll just tell you that it matters. Okay, and then I promised you some unipotent groups. So here's the unipotent group. I just wrote it down as a matrix if I'm in the case of the 7-fold cover. And it's just putting a bunch of identity sub k's on the diagonal, and then an identity sub 2n in the middle. And it's written up in the slide as a bullet. It's the unipotent radical of a certain parabolic subgroup with Levy, a bunch of GLKs and an SP2n. Okay, so it's the kind of thing I'm showing you on your screen. And the character is based by taking the diagonal above the main diagonal and just adding those k by k block matrices and taking the trace of it, and then applying a standard additive character to that. And for those that know unipotent orbits, there's some natural way I can talk about this kind of setup and this character in the language of unipotent orbits. Okay, now when you look at this, you might be a little bit concerned because my character doesn't seem to have anything to do with the middle of this matrix. So what's going on with that? I mean, it doesn't seem like the right thing. The middle of this matrix is what's going to get mapped to the Heisenberg group. So if you look at the middle piece of that big unipotent matrix, that's isomorphic to a Heisenberg group. And so you can let L be a map taken, obtained by first projecting to this subgroup, which is simple to make a quotient which is isomorphic to that, and then using an isomorphism or a homomorphism from this to a Heisenberg group. So in a sort of a natural way, I can make a Heisenberg group, and so there will be an action of the middle piece by the character coming from the Weil representation attached to the Heisenberg group. Okay, so all this algebraic and representation theoretic structure is going to fit together. All right, and now I can write down for you the global integral. And again, there are details, but I hope that the broad structure comes through. So I'll start with a number field containing enough rth roots of unity. And I said I need two representations. I need the Weil representation, and I need a small representation. And if I'm on the R-fold cover of SP, and it happens to be 2n plus k times R-1, what am I going to do? Well, I just take the residue of an Eisenstein series. That's the only thing I can do. And I'll get a representation which is small, but once again is not minimal. And I'll show you the ways that it's similar to and different from the other non-minimal representations that I told you about earlier in the talk. Okay, and I'm going to completely omit from this talk some aspects of covering groups, but I'll mention that to do it carefully, some very nice papers of Shuichiro Takeda and Eyal Kaplan are very helpful because they're very careful about how you handle some aspects of covering groups on an adelic setup. Okay, so here's the global integral, and there's some words here, but the basic idea is the global integral, which the theta kernel is now the product of two different theta functions, not just one. One is a classical theta function attached to the Weil representation. That's this guy, theta 2 psi. So that's a standard thing, and here's the action of the Heisenberg group and the action of this embedding. And then this, or the theta function evaluated at that combination, that group element. And then the second theta function is a theta function on an R-fold cover, which is another guy, again, small but not minimal. And then you do a unipotent integration in the kernel and you put in a character. So that's the object that comes up. And then you can take an automorphic form on one group and in a sort of natural sense, physically move it to the other group by means of an integral, which generalizes the theta integral. Now, and then there's some kappa, which keeps track of even versus odd that's in the notation somewhere. Not too important. Now, you might ask, what about the one-fold cover? So what about the one-fold cover? So in the one-fold cover, this unipotent group turns out to be trivial. And in fact, this theta 1 is a theta function on the one-fold cover, small. You might as well think of it as the function 1. And so in the one-fold cover, this is the standard theta integral. But in fact, for higher covers, you need something different, as you can see. So you need some new ideas. But in the case of the one-fold cover, a lot of the structure degenerates, and you get the classical theta correspondence. Okay, you could also do a lifting the other way from the way I showed you. And if you read the slides carefully, I've gone one way, you could go the other way. Now, I want to tell you a little bit about small. And so maybe I won't, just in the interest of time, go through this in great detail, but there's a conjecture that we make for the smallest non-trivial Fourier coefficients attached to the theta representation. And that is in the language of these partitions. And if you remember, the non-minimal theta correspondences I was showing you, both the one I did with Bump and Ginzburg and the one of Spencer Leslie, involved non-minimal guys which had a bunch of 2s. But these theta, these unipotent orbits are larger. They will have a bunch of R's if I'm on the R-fold cover. And so the exact thing you have to do is you take 2L and you divide by R, and you put as many R's as you can, and then you take the remainder. And you sometimes have to make a little adjustment because that doesn't turn out to be a unipotent orbit attached to a symplectic group, so you need to make a little bit of an adjustment. Okay, so our conjecture is that that's the correct unipotent orbit to attach to this theta function. So again, it's small, but it's not as small as the prior work. And the first part of the slide says that this mimics some observations of Yunqing Kai and independently locally Gordon 7 for the general linear group. And but in the symplectic group, this has not been proved. Okay. And so now I can tell you our main results. So here's what's in the preprint. So the first two theorems are about the Fourier coefficients of these exotic residues of Eisenstein series. And when I was saying that there's a unipotent orbit attached to the Fourier coefficient, there are two parts. First of all, lots of Fourier coefficients are 0. That was what we started talking about, the classical theta functions as having that property. And these objects, these residues of Eisenstein series also have that property. And we can prove that, in fact, all larger unipotent orbits or non-comparable unipotent orbits give Fourier coefficients of 0 for this theta function, which is a residue of the Eisenstein series on the R-fold cover of the symplectic group SP2L, 2L by 2L symplectic matrices, if you want to think of it that way. Okay. The Fourier coefficients, when you say something has a unipotent orbit, you're also making a non-vanishing statement that lots of Fourier coefficients are 0, but at some point they're not 0. And that's where we have a partial result. We can prove our conjecture completely for the 3- and 5-fold covers of the symplectic group. And in general, we can make some statements, but maybe not the most general statement. Okay, so that's what's in the paper. And again, there are some details on the slide, but what I want you to take away is that it looks quite promising for the Fourier coefficient conjecture. And this is a theta correspondence using some new structure, and in particular, these representations that are small, but not quite as small. We also have a theta tower. And again, the first occurrence in a theta tower is cuspidal. And there's a local correspondence as well. And for equal rank and unramified principal series, we prove in our paper that that exotic twisted Jacobi module I showed you earlier does give a local How correspondence in the sense at least at the unramified principal series, those particular representations, which almost everywhere are what you're looking at in the automorphic world, the local theta map is indeed functorial. Undoubtedly, there's much more you can say. Okay, and functorial means with respect to these exotic connected components of L groups, where again, the odd degree covers work like the 1 degree covers, and the even degree covers, for even degree covers, you have to, if there are 2 root lengths, you have to swap short and long roots. Okay, now there's a little bit more structure that I want to elucidate in the last couple of slides of the talk here. And the thing I want to tell you is that this correspondence that we're writing satisfies a non-obvious rigidity property called the dimension equation. And the dimension equation, obviously it's about dimensions, but there are 2 different kinds of dimensions that are playing a role in things like the integral, which is now on the screen in front of you. So I have a bunch of groups that are involved, and I also have these representations, the 2 representations of the automorphic representation before I lift it and then after I lift it. And then there are these representations that occur in the integral kernel. And so the dimension equation, says that there's some rigidity that connects the dimensions of the groups in the integral that describe this transfer map and the dimensions of the representations involved. Now, these representations, of course, are all infinite dimensional representation, but dimension means here in the sense of Gelfand-Kirillov dimension, and sometimes that's only viewed as a local notion, but in Ginzburg's 2006 paper in the Israel Journal, he had a global notion. You should think of it as 1/2 the dimension of the maximal unipotent orbit that supports a non-trivial Fourier coefficient. That's a good definition of it. And it actually even goes back to some notions of David Vogin as well. And so there's some rigidity statement that I've written down for you in the equation that's displayed on the screen. And it says that if pi is what I start out with and I lift it to sigma in the sense of this exotic theta kernel, and in the case where I'm doing them both being generic, then when the ranks are the same, the dimensions of the groups and the dimensions of the representations all fit together. And for dimensions of representations, I have to assume that conjecture about what this representation really looks like in terms of its unipotent orbit. But if you grant me that, then this remarkable rigidity property holds. And that's another aspect of this integral and why one might write down an integral of the kind that we wrote down. And if you want to know more about these dimension equations, they're a beautiful structure that maybe isn't as widely known as it could be. And it really started with David Ginzburg's 2006 paper. And the latest incarnation is a paper I wrote with David that's on the archive in 2019. And we even extend the prior work to include doubling and generalized doubling integrals where the dimension equation didn't fit in to that situation before. And if you look in section 6 of that paper, you'll get more information about the way to think of theta liftings in the context of the dimension equation. Okay, so I do want to allow a little bit of time for questions, but let me just add a couple of final slides to mention some work in progress and some a broader context for this work. So the one thing I didn't mention is whether the lift is non-zero, and we can actually prove something that we're in the middle of trying to write down in full detail. I mean, so one should be cautious until it's all written down, but we're optimistic just to say that we can always prove that a generic hospital representation of SP2N lifts non-trivially to a generic genuine representation. Genuine means it really lives on the cover of this particular orthogonal group. And if you do the one full cover, you say that SP2N goes up to SO2N plus 2. And sometimes it actually you only need to go up to SO2N plus 1. And there's an interesting story related to periods. That's that work of Brooks-Roberts that I mentioned. And so if you're doing this lifting for higher degree covers, the set of groups which can occur, the places where there could be a first occurrence expands. And instead of there being just two possibilities, there turned out to be R plus one possibilities. And so that's something that we're in the middle of working on. And it does look like this idea of allowing unipotent integration should allow us to extend those earlier theta maps, those non-minimal theta maps that I showed you, the one I did with Bump and Ginzburg and also Spencer Leslie's, to higher degree covers. They were only for a double cover or a fourfold cover. And the new idea that's missing is to add this extra structure of unipotent integration. And that's going to hopefully allow us to extend those maps as well. Okay, so just to end my lecture, I'd like to suggest the following broader paradigm. There are lots of constructions in the world of automorphic forms, and they work for algebraic groups. And we've known for a long time that we should, morally speaking, think of the metaplectic group of A, the double cover, as morally speaking an algebraic group, even though it's not literally, and we should expect that to fit into the canon for all sorts of statements about liftings but the proposal is that higher degree representation covering groups should also fit into the story. Now let me right away jump to the statement at the bottom that Marty Weissman has defined a metaplectic L group. It extends that work on the connected component in the split case that we did all those years ago, but it's much, much more involved, and there's a richer theory, as he beautifully pointed out for us. And so you can formulate Langland's functoriality for covering groups. But I'm saying more than that. Not just an abstract statement like functoriality, but a lot of the sort of physical constructions involving automorphic forms, they should also extend to covering groups, but sometimes in a non-trivial way. So 3 examples. Fan Gao, in a great piece of work, extended Langland's computation of the constant term to Eisenstein series for covers. He did so in an algebraic-geometric language of Berlinski-Deligne covers. Then in the last couple of years, I and David Ginzburg and Yunqing Kai and Eyal Kaplan extended the doubling constructions of Piatetsky, Shapiro, and Rawls to not just twisting by GL1, but twisting by GLK, which allows us to prove some instances of liftings, which Jim Arthur proved using the trace formula, and we can prove them without the trace formula because we can use the converse theorem. And Eyal Kaplan was able to extend the doubling integrals to covering groups, and he worked in the split case, and then Yunqing Kai using Berlinski-Deligne covers, really building on work of Yamana, was able to extend the unfolding to non-split groups as well. So those are 2 examples where work extends to covering groups, but in a non-trivial way. And then there's this work that says that this classical theta correspondence, which has been studied for so long, also extends to covering groups. So that's the statement. Now there's another map involving automorphic forms that's very well known, namely Langland-Shahidi theory for covers. Of course, there's also the trace formula. I don't have much to say about that. And people in Toronto certainly are the ones to speak to about that. But I did want to say something about Langland-Shahidi theory. It's not straightforward to extend Langland-Shahidi theory to covers because it involves Whittaker models, and Whittaker functionals are only unique if you work with the groups. If you take the inverse image of a torus in a covering group, it's no longer abelian, and that causes even locally Whittaker functionals to generally not be unique. So it doesn't look like there's so much hope to extend Langland-Shahidi theory. But the proposal is that you should use generalized Spey representations. This is for classical groups. I don't know anything about exceptional groups, but for classical groups, you should be able to use generalized Spey representations. And then Suzuki, for the general linear groups, conjectured that a certain generalized Spey representation would have a unique Whittaker model. And we are proposing that there should be an extension of Suzuki's conjecture to other kinds of groups beyond the general linear group. And then that you should be able to study Eisenstein series attached to these generalized Spey representations, and then extend Langland-Shahidi theory to covering groups. So that's all work to be done. And at least it gives a sense that maybe the study of extending these constructions to covering groups should be possible, and maybe there'll be some interesting number theory there. And so that's the last thing I wanted to say, but thank you very much for listening. And I do look forward to seeing everybody in Toronto someday when this is all behind us and we can go visit each other again. And in the meantime, it's so wonderful to see everyone electronically. Thank you.
Thanks all very much. I don't know if you can hear us, but we're applauding you.
I appreciate it.
Very
Maybe I'll
quick.
leave the screen sharing just up for a minute in case any of the slides turn out to come up.
Very clear talk, very interesting and even inspiring results. I really like them very much. Unfortunately, I have to run off to another meeting right now, but I wonder if there's a quick question somebody can take over for me. And are there any questions from the audience? So let me ask, if you don't mind, let me ask a quick question. So this construction now, you've shown that in some cases it's non-trivial. And do you get any cases where you can recognize the transferred L function in some form, that something that you would expect, something friendly, classical, that you get an integral representation for?
That's a really nice question. And I think what we all expect is that there should be a generalized Shimura correspondence. And that's not been proven. I mean, in the 1980s, Kajdan and Flicker and Patterson were all heavily involved with thinking about that. Flicker was able to make a correspondence for arbitrary degree covers of a certain GL2. There are different covers for the right one using the trace formula and matching orbital integrals, but even there, it's not obvious what it means in the language of Fourier coefficients, which of course is what we certainly want to know. And for higher degree covers, it's not obvious. So, you know, if you see an L function, you know, with an honest to goodness Euler product, then we expect it's an automorphic L, and you know, and the usual properties that it's an automorphic L function, and there should be some kind of a Shimura correspondence. So such things came up, for example, in Van Gao's work. Let's see, on extending Langland's work on the constant term. But here we're actually picking up the automorphic representations themselves. So we're not making L functions, we're actually taking a representation on one group and making a representation on another. And again, the analog would be the classical Shimura correspondence. And so indeed, as you know, Waltz-Bourget did show that there's something tremendously interesting about looking at the Fourier coefficients in that context. And I don't think we know enough at this point to say anything. But the broader context of studying the generalized Shimura correspondence is very attractive. One certainly will need tools beyond those that were available in the 1980s. But and Wenwei Li was able to do it in some limited cases. I think he's even talking about that tonight in a Pacific Rim seminar. I'm hoping I can stay up late enough to watch it. But I think in general and for higher degree covers, most of this is really not known.